Welcome to this deep dive into the incredible world of integer sequences. Today, we're zooming in on a really key resource for anyone studying number theory, the OEIS, the Online Encyclopedia of Integer Sequences.
It's an amazing tool, absolutely essential.
And specifically, we're looking at sequence A000204. These are the Lucas numbers, the version that starts with 1.
Ah, yes, A000204, a classic sequence. It's defined by a recurrence relation that, well, probably feels quite familiar to many listeners.
Exactly. It's got that Fibonacci feel, right? Each number is the sum of the two before it. ln equals ln has 1 plus ln2.
Precisely the same rule. But the difference, the crucial bit, is the starting values.
Right. For this sequence, A000204, it kicks off with L1, L2 equal 3.
And that's important to pin down because you'll sometimes see Lucas numbers defined slightly differently. The OEIS actually points this out, referencing A00000032.
Ah, the one starting L0 to L11.
That's the one. L0 to L1 all 1, which gives 2, 1, 3, 4, 7. Very closely related, of course, they share the same recurrence. But starting differently means they are, strictly speaking, different sequences with some different properties down the line.
Good point. So just to be clear for everyone listening, today we're sticking with A00000204, starting 1, 3.
Exactly. 1, 3 it is.
So let's get into it. We have 1, 3, then, okay, 1 plus 3 is 4.
And 3 plus 4 is 7.
4 plus 7 is 11.
7 plus 11 is 18.
11 plus 18, 29. And it keeps going like that. You can really feel that additive structure, just like Fibonacci.
It's the core mechanic, definitely. And just a quick note for navigating the OEIS itself with this sequence, A000204 is indexed starting from N1, so L1 is the first term listed.
Got it. N1 gives 1 and N2 gives 3.
Makes sense.
Now, one thing I love about the OEIS is how these sequences wear different hats, you know?
Oh, absolutely. They show up in unexpected places.
Like this one's apparently also called Shout's Accessory Series.
That's right, an older name. It pops up in some historical texts, but perhaps more intuitively graspable are the combinatorial interpretations.
Okay, like what?
Well, Ln actually counts the number of matchings in a cycle graph with n vertices.
Matchings in a cycle graph.
Yeah.
Like pairs of edges that don't touch.
Exactly. Pairs of non-adjacent edges or single edges or even the empty set no edges selected counts as one matching too.
Huh. Can you give an example?
Sure. Take N4, that's a square, right? L4 is 7. If you draw a square, you can count the ways. Choose no edges, 1 way. Choose 1 edge, 4 ways. Choose 2 opposite edges, 2 ways.
So 1 plus 4 plus 2, that's 7. Wow.
It works out perfectly. It gives a very tangible meaning to the number 7 in this sequence.
That's really cool. It makes it feel less abstract. And the OEIS mentions generalizations too, something about covering rings.
Yes, it relates to covering a ring lattice. Think of points arranged in a circle with molecules of a certain width, m. For our Lucas numbers, m is 2.
So it's like placing dominoes on a circular board.
Sort of, yeah, related to tiling problems, and this naturally connects it to other sequences where m is different, like 3 or 4, which have their own OEIS entries. It shows it's part of a bigger family.
Interesting. And then there's a link to dynamical systems. That sounds quite different.
It is, but it's a fascinating connection. LAN counts the number of points that have a period of exactly n in something called the golden mean shift.
A chaotic system, right?
A specific kind, yes. It's pretty remarkable that the count of these periodic points is given by this relatively simple integer sequence. And there's another sequence, L06206, that counts the orbits of these points.
Wow. Okay, and what about like computer science stuff? Binary strings?
N, which is our Ln, counts the number of circular binary strings of zeros and ones arranged in a circle of length and that don't have two ones next to each other.
No consecutive ones in a circular string.
Exactly. So for N5, L5 is 11, and you can, if you're patient, list out the 11 5-bit circular strings without 11 appearing, like 0100 or 1000 or 0000.
Okay, I'll take your word for 11. That's quite versatile. It also pops up in row sums of certain triangles, A029635 and A1825779.
That's right. Just another place these numbers make an appearance, showing how interconnected these numerical patterns can be.
So shifting gears a bit, what about pure number theory properties? Modular arithmetic.
Ah, yes. There are some elegant properties there. A key one mentioned in the OEIS is related to primes. If p is a prime number, then LP is congruent to 1 modulo p.
LP leaves a remainder of 1 when divided by p.
Precisely. So L3 is 4, which is 1 mod 3. L5 is 11, which is 1 mod 5. L7 is 29, which is 1 mod 7. It holds.
Neat. And there's one involving powers of 2.
Yes, attributed to Thomas Swerdowski. L2k is congruent to Mattis 1 modulo 2k plus 1.
So like L21, L2, 3, and that's Mattis 1 mod 2, 1 plus 1 equals 7. Is that Mattis 1 mod 2 plus 1 equals 8? Yes, 7 is congruent to Mattis 1 mod 8.
Exactly. These kinds of congruences are, really useful tools for studying divisibility properties of the sequence.
Okay, we can't really talk about Lucas numbers without talking about...
Fibonacci numbers.
Right. A00000045. They're like siblings, aren't they?
Very close siblings. They share that fundamental recurrence relation. The OEIS lists several key identities connecting them.
Yeah, I saw ln plus fn plus 1.
That's a fundamental one. It shows how a Lucas number is sandwiched between two Fibonacci numbers, or you can write it as ln 2fn plus 1 fn.
And there are others, relating terms with doubled indices.
Like f2nn, fn, the nth Fibonacci times the nth. Lucas gives the 10th Fibonacci.
Wow.
And also 5fn nu plus 2 times -1n. Or alternatively, ln to 2 times -1n. These identities really show how deeply intertwined they are.
You can even define Fibonacci numbers using Lucas numbers, right?
Yeah.
Fn, ln1 plus ln plus 1.
That's correct. It shows the relationship goes both ways.
And underlying both is the golden ratio of phi.
Phi, yes. Just like Fibonacci numbers, Lucas numbers have a beautiful closed-form expression involving phi. It's ln fn plus 1 phi.
Where phi is 1 plus square root 5, 2,
Yeah.
and 1 phi is, so that's negative 1 phi, isn't it?
Yeah. It is. So you can also write it as ln aus plus an, or using phi's conjugate, ai, which is 1 square root 5, 2, the formula is simply ln plus n.
It's kind of mind-bending that this sequence of whole numbers comes from adding powers of these irrational numbers together.
It is. And what's more, for n greater than 1, ln is actually the closest integer to n.
Really? So n is always just a tiny bit away from a Lucas number.
Almost exactly. Since the sin term, n-1n, gets very small very quickly as n increases, n gets incredibly close to the integer l, it highlights that exponential growth driven by phi.
Okay, let's talk generating functions. These are like compact ways to represent sequences.
Exactly. They encode the entire infinite sequence into a single function. For the Lucas numbers starting L0 to L1, the generating function is xx 1 by 2.
And that denominator, 1 by n by 2, that looks familiar.
It's the same denominator as the Fibonacci generating function, which is sx 1 by 2. That shared denominator reflects a shared recurrence relation.
Makes sense. The OEIS also mentions a partial fraction decomposition.
Yes, cx equals 1, 1, 1 plus 1, 1x. This form directly connects the generating function back to the closed form Binet formula involving f-band that we just discussed. It's often easier to work with for analysis.
Right. Now, what about Lucas primes?
Ah, an interesting subset. These are simply Lucas numbers that happen to also be prime numbers.
Like L2, that's prime, L4 equals 7, prime, L5 equals 11, prime, L7 equals 29, prime.
Exactly. Though, a small warning, often when people talk specifically about Lucas primes, they use the sequence starting 2, 1. So L02 is often considered the first Lucas prime. The OEIS entry A000204 lists them, but you need to be mindful of the starting point.
Okay, so the indices might be slightly different from our A000204, but the numbers themselves, like 3, 7, 11, 29, are primes found within the Lucas sequence structure.
Correct. And finding new, larger Lucas primes is, an ongoing area of interest in computational number theory. There are lists of the largest known ones.
Is there any rule about which ln can be prime?
There's a necessary condition. If ln is prime, then the index n must be 0, or a prime number, or power of 2.
Oh, interesting. So L6, 18, definitely not prime, and 6 isn't prime, or a power of 2. L8 equals 47, which is prime, and 8 is a power of 2. L9, 76, not prime. It's not a guarantee, but it narrows down the search.
Precisely. It's a necessary condition. Not sufficient, but very helpful.
Now, here's something I found surprising. Sunflowers.
Chuckles lightly.
Yeah.
Yes, it seems a bit out of left field, doesn't it? But apparently, if you analyze the spiral patterns in sunflower heads...
You usually hear about Fibonacci numbers there.
You do. They're the most common pattern. But a 2016 analysis found that Lucas numbers are the second most common pattern for the number of spirals going clockwise versus counterclockwise.
No way. So nature uses both Fibonacci and Lucas.
It appears so. It suggests these sequences might relate to optimal packing or growth strategies in some fundamental way.
That's really amazing.
Oh, okay.
Okay, one last connection, mentioned briefly. Continued fractions.
Right. Powers of the golden ratio should have continued fraction expansions where Lucas numbers appear in the structure.
So, yet another link between Lucas numbers, phi, and a different area of number theory,
Exactly. Continued fractions give very good rational approximations, and the fact that Lucas numbers are involved just highlights again how central they are to the mathematics surrounding phi.
Wow. Okay, so just to recap this whirlwind tour of A000204, we started with the simple definition, Ln plus Ln2 with L1, L2, 3.
We thought its tight relationship with Fibonacci numbers through various identities and the shared link to the golden ratio via the Binet formula.
And we explored some really diverse interpretations, matchings on cycles, points in dynamical systems, binary strings without consecutive ones.
Don't forget the modular properties, like LP being 1 mod P, and the existence of those special Lucas primes.
And even that surprising appearance in sunflowers. It's quite a resonate for one sequence.
It really is. And A000004 in the OEIS is your gateway to all this and more. The references and links there can take you much deeper.
So here's something to think about as we wrap up. We see how Lucas numbers, starting to slightly differently from Fibonacci, carve out their own unique identity and appear in distinct ways.
It makes you wonder, doesn't it? What other subtle variations in definitions lead to entirely new patterns? What other hidden connections are waiting within that vast landscape of integer sequences the OEIS catalogs?
Definitely food for thought. We really encourage you, the listener, to dive into the OEIS, follow the trails from A000004, and see where the numbers take you. There's always more to discover.